Okay, so there are three things that we're going to be looking at today. The first thing is these simulation problems. So if you take a look here, we have researchers believe that the average body temperature is below the commonly believed 98.6 degrees Fahrenheit. A sample size of 50 volunteers has an average body temperature of 98.4. Below is a simulation, and we ran the simulation assuming that the true mean was 98.6 degrees, and we actually did 1,000 samples of size 50 when we did the simulation to figure out if our sample is something that seems a little bit strange based on the assumption. So we're actually going to use this simulation to run a hypothesis test. So you want to think about the different pieces of a hypothesis test that you usually have. So usually you have the null and you have your alternative. So our null would be that the true mean was 98.6 degrees Fahrenheit. Our alternative, this group of researchers think it's actually below. And then remember, we would define our parameter here. So our parameter here is the true mean body temperature. Okay, so normally after we do this, we would either do a test or a confidence interval, but a simulation is actually another way to do it. So when we do this, we think about the sample. So in here, remember, in our last unit, our sample was a p-hat because it was a proportion. Here, our sample is an x-bar because it's a mean. So the sample that we observed would be 98.4. Excuse me. And that's why there's this little flag here, because that's going to allow us to count up the amount of times we observe a sample that has a temperature of 98.4 or less, which is what our alternative is here. So here, if we count these up, these red dots, we're going to get 28 samples in the simulation. Remember, each one of these dots is an average of 50 volunteers. And if you go back and you think about how many dots there are here, they tell us there's 1,000. So it's 29 out of 1,000. So that is really what a p-value is. How, given the null is true, which is what we assumed, and then we ran the simulation, how often do we get something equal to our sample or less? So here, if we think about this value, that means our p-value is equal to 2.9%. So based on that p-value, take a minute to think about, do you have evidence to reject the null, or do you fail to reject the null? Remember, when my p-value is low, I reject the null. So because my p-value is low, I reject the null. I have evidence that the true mean body temperature is less than 98.6 degrees Fahrenheit. Okay, so the example below this is something similar, and I'd like you guys to try that as a practice problem. Okay, I want to get to the next type. So the next thing we need to think about is determining sample size from margin of error. So remember when we did this before, the margin of error for a categorical was your critical z, and you took the square root of p hat, q hat over n. And remember, if we didn't know what the p hat was, we played it safe by using 50% for our p hat. Okay. Now, using that same idea, if we're talking about something quantitative, we would really want to use critical t. Remember, n minus 1 comes from the degree of freedom. And then it would be s over radical n. Now, this piece here, remember, is your standard error of your x bars. Okay, just like this piece was standard error of the p hats. So here, the problem is when we want to find what size we would need for a sample, that means we don't know the size of the sample. Well, the issue with that is that our remember, our t distributions change with the size of our sample because of degree of freedom. So I have a nice simulation I'm going to show you guys in class tomorrow. But for right now, I'm going to just help you guys try to understand this by the fact that as our sample size gets really big, remember we said our t distribution, the tails get less and less fat, and it starts to look very similar to a normal distribution, which means that your t-scores start to approach the z-scores. So when we're trying to determine sample size and we're trying to find something that's a quantitative margin of error, we actually have to use a critical z-score because we don't have any other way to be able to find a critical t. And we know that as n gets large anyway, the critical t gets very close to the critical z. So if we look at this question up here, we have researchers that want to estimate the mean cholesterol level for a particular variety of monkey within 1 milligram per deciliter. And they're talking about 95% confidence. And they have a previous study where they think the standard deviation is about 5 milligrams per deciliter. So what we're going to do is we're actually just going to use the critical z for 95% confidence interval. And we wanted that equal to our margin of error. So here, the margin of error that we were going with, we wanted it to be within 1. So then this is going to be 1.96. Remember, that was the critical z we used for 95% confidence. And then the standard deviation given in the question was 5. And this is over radical n. So then remember, you can use your solve feature on your calculator to solve for n, or you could solve for it by hand. When we do this, we get n equals 96.04. Remember, anytime we have something that's not a whole integer, we have to round up to be on the safe side for selecting our sample. Okay, so that was the second thing. We have one more thing, and then we're done for today, and you guys can work on the practice problems from the homework. Okay, the last thing we need to do is there's computer printouts for these same types of problems. So they tell us that the level of dissolved oxygen in a stream is an important indicator of the water's ability to sustain aquatic life. The researcher measures this dissolved oxygen level at 15 randomly chosen locations along a stream, and a dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. So you need to think about what would your alternative be and what would your null hypothesis be. And it's going to be, you know, the same type of thing that we would normally think. And actually, here in this printout, I don't know if you guys think about this. If you look, it says test of mu equal to 5 versus less than 5. So they actually kind of give it away in the printout. So when we do this, let's not type it. Let's write it. We would be saying something like mu equals 5 milligrams per liter. Mu is less than 5 milligrams per liter. And then you would also need to define mu. Mu is going to be this, the average level of dissolved oxygen in a stream. Okay. Now, normally then, after we do this, we would have to test our conditions. So here they're telling us the conditions could be met. The last thing that we would normally do is we would do our math. We would find our t-score and we would write our conclusion. So if you notice here, they give us the t-score. They give us the standard error of the means. They give us the standard deviation of the sample size, and the mean of our sample. So we can label that for ourselves. So n is the sample size. Let's see if this lets me move this. There we go. So n is our sample size. The mean is x bar. That was our sample. This is this little s standard deviation of our sample. And then this is the standard error of the means. Okay. This is our t-score. And this is our p-value. So if we were going to try to like fake the work to show it from this, we'd be doing the mean minus the proposed mean. So it would be 4.771 minus 5 over, and then normally we would do S over radical N. So we can pull that 0.940 over radical 15. Or if we wanted to, instead of this, we could just put the standard error of the means because those are going to be one and the same. Okay. Then we have a p-value of 0.1881. So that's a p-value of 18%-ish. So based on that idea, because our p-value is high, we fail to reject the mean. So let's type that up. So because our p-value is high, we fail to reject the null. We have evidence, or we do not have evidence. And remember, we don't have evidence to support our alternative because the p-value was so high. So we do not have evidence. The true mean, let's see, dissolved oxygen level is less than 5 mgs per L. Okay. So it looks like this, according to this, the aquatic life should be safe. Okay. So at this point, that's all we needed to get through today. Thank you for watching the video, guys.